Hey everyone, this is Mayur. Welcome back to ML Works. In this video, we'll understand what is KV caching and how it makes the transformer fast during inference. So before we get into KV caching, I would recommend watching this video from Umar, which talks about the transformer architecture. Because without understanding the transformer architecture, you cannot understand KV caching. So you can watch this video on the specific link mentioned in the slide. So let's get into KV caching. So what's the issue with transformer, right? So consider the models like GPT models or Llama 3 models or any other such large language model. They have an architecture which is very complex, and the size of the model itself, right, it is quite huge because the number of parameters they have, it is quite large in number. So when you are trying to deploy such a model for certain applications like chatbot, the time taken for one query to get the response is quite high. Now to avoid that, there is a trick called as KV cache, which tries to avoid certain matrix multiplication operations for generating the token. It tries to avoid certain matrix multiplication operation. So this whole thing happens in the decoder network of a transformer. So because decoder is the module in transformer which tries to generate the tokens for a given input in a large language model. So where KV cache is applicable, so as I said, it is on the decoder aspect of your transformer architecture. So KV caching occurs while generating multiple tokens generation, and it only happens in decoder network. So just to give an example, you can take ChatGPT, and if you type in certain keywords, just type one word, right, it will automatically explain the next the query that you have passed. It generates the multiple tokens. So that is happening because of the decoder part of your model. So here if you see on the right hand side, you have this encoder which takes in the input, and there is another part or module called as decoder. And here you have something called as multi-head attention, and if you look into multi-head attention, there is something called as scaled dot product attention, which takes in three inputs, which is query, key and value. And if you go inside scaled dot product attention, you will see a bunch of operations happening between query and key, and then it is scaled, then it is masked optional thing, and then you have softmax, and then that result is multiplied with the value and you get a final result. Just to reiterate, in decoder only models like GPT or decoder part of the encoder decoder architecture like T5, we use KV caching, and models like BERT, which is an encoder architecture, doesn't use KV caching. So BERT is nothing like what you can use it for downstream tasks like classification, and there we cannot apply KV caching. So transformers, decoder, KV cache. So decoder works in a auto-regressive fashion. What do I mean by that, right? So consider here you have this input, recite the first law, and that is a starting token which is light blue in color, right? So this is passed as an input to GPT-2, and it will generate an output A. And that output is taken as an input along with the rest of the input, and then it will generate the next token, which is robot. Then those two inputs again taken as an input along with the rest of the input, generates the third token May. This is what auto-regressive way of generating tokens or generating the next token. So if you see here in the definition part, in the auto-regressive generation of the decoder, given an input, the model predicts the next token, and that token is combined with the rest of the input to generate the next token again. So there is certain repeated calculation that is happening if you see. So first let's understand this part right here. Recite the first law, and this 5 tokens are, this is the 5 token, first 5 token. Then you generate A. This is the new token that got generated. Now why to use the calculation done for this specific input again? Why to calculate again, right? The matrix calculation, why to do it again? You can directly use the previous value generated for these input and store it somewhere, and just use the new token that got generated, A, robot, and try to generate the new values, key, query and key value for that. Okay, that's what here it refers to, right? If you see here, here we can better understand this by zooming in on the masked scaled attention, that is a calculated in the decoder part, because there is a certain behavior that is repeated. Okay, so we'll see that in the next slide. Okay, so let's understand this part. Okay, step 1, you have query token 1 which is getting multiplied key token 1, and then you have query token 2 which will get multiplied with key token 1 and then key token 2. So it is getting multiplied with this one and again key token 2. 3 will get multiplied with 1, 2, 3. 4 will multiply with 1, 2, 3, 4. Okay. So at the end it will again get multiplied with value token for 1, 2, 3, 4. Okay. This is what actual calculation that is happening in decoder architecture. Now, so let's understand this part. Like the decoder is causal. By that it means the every input that is getting generated, it depends on the previous input. Okay, as we saw, a robot may. Okay, the robot depends on the previous input, a token. Okay, so here if you see, since the decoder is causal, the attention of a token only depends on the preceding token. At each generation step, we are recalculating the same previous token attention. Okay, there are like some calculation that is happening which are like recalculated continuously. So when we actually just want to calculate the attention for new token, which is the A, for a robot, okay, the robot token, A is the new token, and for May, robot is the new token. By that I mean, so A is the new token for generating robot. Robot is the new token for May. Okay, so that's the point here. Okay, this is where KV caching comes into play. It catches the previous key value states and focuses only on the attention of new token. Okay, so let's see here, right? Step 1, without caching, what will happen? So you are trying to calculate without caching, and it has to generate, see, Q1 K1, Q2 K1 and Q2 K2, and for every token that is passed, this is happening. Okay, so for every token that is passed, it has to do all these calculation again and again. Q1 K1, Q2 K1, Q2 K2. For token 3, it has to do Q1 K1, Q2 K1 and Q2 K2, and Q3 K1, Q3 K2, Q3 K3. Okay, it has to repeat so many times, right? The same set of operations. So when you cache it, if you see here, so Q1 query 1 token is given, K1 is taken, and you generate this one, and you are not repeating certain calculations here. Okay, so when you are passing the Q2, you are not calculating Q1 K1 again. If you are passing Q3, then you are not calculating Q2 K1, Q2 K2. Okay, so certain operations are avoided. Okay, because we have cached those values somewhere. So at the end, what we do, right? We try to reduce the number of operations that is happening while trying to generate the next token. So why is this optimization important? As seen in the picture above, the matrices behind the KV caching are way smaller, okay, which leads to faster matrix multiplication. The only downside to this is, okay, we have to store this key value pair in somewhere in the CPU RAM or GPU RAM. Okay, so that is the storage part that comes into picture. So here is the coding snippet for KV caching, where we are trying to use a Hugging Face library transformers. And if you see here, first what we do is we check if we have CUDA or not, and then we take the tokenizer for GPT-2, and then we load the model GPT-2, okay, and attach it to the device if it is on GPU or CPU, whatever it is. So we are running two states. One is true and false. True means like you are using the cache. False means you are not using the cache. You are trying to generate 10 generations. For 10 generations you are doing, and what is the time taken for that? Okay, so model.generate, you are passing the tokenizer, first passing the input through the tokenizer and then to the model. And if you see here, based on our first scenario, which is true, use caching. Okay, it will cache the output of certain matrix multiplication. It will cache those values and it will generate the response. And you are just getting the end time and storing it somewhere. Now, in the second scenario, where the caching is false, you will be not using cache and you will be repeating the same calculations again and again. So based on that, if you see here, With KV caching, it takes around 11.885 seconds plus or minus 0.2. And without KV caching, it takes around more than, it is 5 times more, okay, into 5 times of this. Okay, so it is taking almost 5x, okay, when it comes to what doing an inference. So that's how what KV caching tries to reduce the time taken to do an inference while you are sending an input, right? So this is the end of the video where we understood, okay, what is KV caching and how certain matrix multiplication values, okay, can be cached such that those operations are not taking place again and again. So with that, I'll conclude this video. Thank you for watching.